Okay, I'm going to try to show you a couple examples of a single ANOVA and a chi-squared distribution. So let's take this example that we've got a bunch of average freshman SAT scores in various different disciplines, architecture, business, education, and we want to understand if there's a statistical difference in the SAT scores of our students. Well, just to get an eyeball, we could go up here to function and put in an average. And it's going to average those, and we could fill it over to the right. So eyeballing this, there seems to be a pretty good difference. Let's highlight that. Pretty good difference between our engineering students, which is a 1200 SATs, and our health sciences 975. There seems to be some sort of difference, but remember, since we have multiple criteria, now if we were only comparing two, we could use our t statistic, we could calculate our sample standard deviation, etc. But since we have multiple areas that we're trying to compare, we'll want to use an Anova test. So to do an Anova test, we go to Data, Data Analysis, and we're going to do Anova single factor. And it's going to ask us for what is the range. So let's put in the range. So our range is going to be all of this data right here. And we do have the labels, and let's do it. The labels just mean that I included these titles. And our alpha will be 5.05. And let's put the output range right there. That looks good. And now we just hit OK. And we get this type of information. So here's our different groups, a count. Of course, we had a sample of 4 in each one. It gives us the sum, gives us the average, which you can see is the same average as we calculated here. And it gives us the variance, how much deviation there is. Because what we're going to do is we're going to compare, and there's other videos on this that'll explain it better, but we're going to explain the difference between whether the source of the variance is between the two groups, in which case we have a difference between groups, or is it within the groups, which is comparing the different variances of each group. So if we look over here, we got some very important numbers. First, we have an F score. So that is basically our test statistic. We got a score of 234, which means we're pretty well out on the curve. Our p-value, you can see, is 3.9 times 10 to the negative 18. That in Excel, e to the negative 18 means 10 to the negative 18. So we've got 0.00000, an extremely small p-value, which means that if you remember, the probability of this happening by chance is almost 0. And our critical F is 2.5, so the 234 is way outside that region. So we can reject the null hypothesis that there is no difference amongst these. And we've proven with the ANOVA, in other words, you'd use the ANOVA when you've got multiple things you're trying to compare. And we've proven that, yes, there is a statistical difference between the SAT scores of the engineering school students and the health sciences. So the ANOVA we're going to use when we have more than two variables that we're trying to compare. Now let's talk about the chi-squared for a second. Let's assume ExxonMobil, now we have more categorical data. Let's say ExxonMobil wants to determine if premium gas sells more with high-income customers rather than low-income customers. So we've got three sets of customers, 0 to 40,000, 41, etc., and two types of gas, premium versus basic. So here's our observed value. How many people bought premium? How many people bought basic? Now the expected value in the gray, I've calculated it for you, but just to remind you the calculation, you would take the total of the row times the total of the column divided by the total. So done all that math to calculate. So what this is saying is we actually had 2,500 people that make under $40,000 bought premium gas, but we would expect 2,478 to buy it, and etc. Here we calculated the chi-stat, which is very much like your F-stat or your T-stat. And what we did is we compared how many people actually bought it minus how many we expected to buy it. We squared that number, so we got a positive number, and we divided it by what we expected. So it's the difference between what we actually got minus what we expected squared divided by what we expected. And we do that for all those squares. We total it up, totaling all of our individual chi-squares to get basically our chi-squared stat. Our critical value, again, we can go to Excel and use our INV tool. Remember, that's where we find our critical value. So it's a chi-squared INV, right tail, 0.05 level of significant, 2 degrees of freedom. Remember, our degrees of freedom is the number of columns minus 1 times the number of rows minus 1. So we've got 2, 3 minus 1 times 1, 2 minus 1. 2 times 1 is 2. That's how we know we had 2 degrees of freedom. This gives us our critical value. Notice we are not outside the critical value, so we do not reject that there is a difference. And our p-value is 72%, so there's a 72% chance that this would happen by chance. So we do not reject that there's a difference. But let's play around with the numbers for a second. Let's make this, let's make our high income, let's say they bought 9,000. Now, before I hit enter, we should expect, now we're probably going to reject our null hypothesis, i.e. our grand total or our test statistic will be outside the critical range, and our p-value will be very, very small. And that's basically what we got. We're way outside the range. We're way outside, you can see the critical value is and the p-value, is essentially 0. Let's try another one, 5,000. There we go. Again, we're way outside the range. Our p-value is something times 10 to the negative 51. So it's extremely small. So the odds of getting these are very, very small by chance. So we would reject the null hypothesis and say, yes, there is a difference in income in what type of gas they buy. So there's an example of the single ANOVA and the chi-squared. If you have any questions, let me know.